Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks. Okay, so I'm going to talk mainly about what was in my thesis, but that leads on to my 5-year master plan. My thesis was really about pushing separation logic to reason about Java. So, really to reason about Java, you need to reason about modularity, because it's object-oriented languages, sort of basis of them is modularity. And the previous work on separation logic, there wasn't really any abstraction or modularity going on. So the only sort of prior work was by Peter O'Hearn, Hong Sok Yang, and John Reynolds, where they kind of had a bit of modularity, but it was very static and didn't capture any of the modularity that you get in a Java-like language. So in this talk, I'm going to start out by just sort of describing some dynamic modularity. So this is where you can dynamically instantiate data types, and they're kind of dealt with as abstract data types. And I'll do this through a sort of similar notion of predicates. And then I'll show how to extend separation logic to allow sharing between these data types, and then go on to actually reasoning about classes where you have inheritance. But before I tell you this, I should probably tell you a bit about separation logic. So separation logic is Hoare logic plus a few bits. So the first thing is the separating conjunction star. So this P star Q means that we can split the state into two pieces, one of which satisfies P and the other part satisfies Q. So this splitting is essential for when you're wanting to talk about framing, because you want to actually say things are separate. So how do we actually say something's in the heap? So we say E dot F points to E prime, so that the heap contains a single field F of an object E, and its value is E prime. So now we can actually build up heaps that talk about many fields by just starring together individual fields. So separation logic is slightly different to Hoare logic in that it has this safety property. So whenever we just say a specification PCQ holds, the P must specify everything that we're actually going to access in executing C. So this leads to the powerful rule of Hoare logic, the frame rule. So if we can prove that PCQ holds, then we can extend it with any disjoint piece of state, and we know that disjoint piece of state will be unmodified, because we know that everything that C will touch was in P, so we know that anything separate from P won't be changed. So this is the real sort of essence of local reasoning that separation logic gives. We can just talk about what we're going to do, and then we can extend it to the situation we actually are working in with extra state. So just to sort of highlight this difference, so in Hoare logic, we write if x gets E, then we can just write this substitution P with E for x, P with E for x, and the postcondition is P. So this means we can say things like, well, if y equals 7 and we assign x 3, then y still equals 7. But we haven't mentioned x anywhere in this triple. Now we can't do that in separation logic when we talk about fields. So the field assignment rule is that we need the field to point to something. So I use underscore when I don't care what it is, so it's just an existentially quantified value. So if I want to assign E to this field, then I need to know the field exists, and afterwards I know it has the value E. So this means we can't say assign some field 3 and say, well, this other field equals 7 before and equals 7 afterwards, because we haven't mentioned the field we're actually altering. So this is where the safety property comes in, that we must describe everything we're going to touch before in the precondition. Okay, so now on to abstract data types. So if we want to reason about abstract data types, we need to somehow scope their definition. So if we think about abstract type, the abstract data types from a type point of view, we have a type name and a signature. And inside the module that defines the abstract data type, we can freely think about the signature and the type name together as kind of the same thing. But outside the scope of that module, we just think solely in terms of a type name. So if we're going to do the same thing in logic, we can think about a predicate name and a predicate definition. So inside the module, we're going to think about just the predicate name. Sorry. Inside the module, we're going to think about predicate name and the predicate definition. And outside the module, we'll just think about the predicate name, and we won't be able to fiddle with it. So we can give, whenever we think of our kind of environment now, so we've got our gamma, which represents kind of procedures, and we'll have some lambda that represents actually the predicates we know about at the moment. So then we can just sort of, lambda is just going to be a sequence of definitions of predicates alpha 1 to alpha n, which take some arguments and have some definition. So whenever we know a predicate, so if we have a particular predicate around and we have an instance of that predicate, then we know we can exchange it with its definition. And conversely, if we have the definition, we can exchange it with a predicate name. So this is kind of within the module scope. We can freely exchange between what the definition is and what the name is. But if we didn't have the definition in this lambda, then we wouldn't know anything else. So we wouldn't be able to do this exchange because we don't know what we'd be exchanging with. So that's like, so when you're inside in the type world, when you're inside a module, the type name and type signature are just really seen as the same thing, which is really just two implications, say equality. But outside, we just have the name. So we can give a kind of scoping rule to this that says, so this is just sort of given in procedural context, but obviously we can apply it to a Java-like context, just for compactness. So if we want to verify some procedure K1 with parameters and body C1, then we can verify that knowing some extra definitions. But when we actually come to verify the client code C, we don't know that those extra definitions in lambda there. So we're just reasoning. So this is really capturing that scoping I've been talking about. So we can do this rule, and now we've got kind of reasoning about abstract data types in separation logic. So let's go on to a quick example. So I'm going to talk about database connection pools. So a database connection pool, well, constructing a database connection is very expensive, so we don't want to do it often, so we'll try and reuse them as much as possible. So we'll assume that we can actually, the environment somehow lets us create a database connection con to some database DB. And we don't care what actually a connection is when we write a connection pool because, well, we just want something that represents a connection. So we're going to define some predicate pool to represent one of these connection pools, but the client of the connection pool won't even know what pool is. They're just going to be completely independent of all these definitions. So we can think of a pool with a simple specification. So we have some constructor which starts out with requiring no heap and creates a pool for the database it's constructed for. And we have a get connection which, given a pool predicate, gives us a pool and a connection. And we have a free connection that, given a connection and a pool, gets rid of a connection. So we just have a pool afterwards. So this is kind of a fairly abstract specification of what a connection pool does, but it's hopefully fairly natural to actually reasoning about a connection pool. So we can actually define the fields of a connection pool. So if we have some database field and a connection list, and then we'll have a connection list which is just a head which will be a connection, and then some tail which will be another connection list. So we can define what these things actually are in separation logic formula as just being, so that for a pool, the DB field points to a database, and the list field points to a connection list. And for a connection list, either it's empty, so X is null, or its head is a connection and its tail is a connection list, and they're both of the correct parameter DB. And in this, we've not had to worry about what the definition of connection is. We're just saying con, so it's abstracting that. So we could go away and we would need to verify some of the actual bodies of these methods. So I'll do the simplest one so it fits on the slide. So if we were to verify the constructor, then all that does is assign the DB field, the DB parameter, and the list field null. So we get that we have to prove this implication, so that the database points to DB and that the list points to null, so that is actually a pool, because the post condition was that we needed a pool. So we can take the connection list and pool and just, because we know the definition, we can say, well, empty implies connection list, because that was one of the cases in the connection list. And we know that if we have a database and a list to a connection list, and that's pointing to some value, and that value is a connection list, then we have a pool. And then we're done, and that's just wrapped it up as we need. So outside, when we're in a client, now we don't know anything about these predicates. So they're just completely abstract. But we can quite happily verify this code so far. So we start out, we call new on the pool, we get some new pool on some database. So then we get the pool predicate, and we can call get connection. So this gives us a connection we can use. Then we can actually use the connection and do something. And then we can free the connection. When we get to the end, we can't actually use the connection now, even though this connection is in our precondition, because we don't know it is, because we don't actually know what pool is. So we've gained some modularity because we don't know what this definition is. We've prevented people from accessing things, even though it is kind of in the precondition. And that's exactly how it should be, because if we did depend on a particular way the pool had been implemented, we wouldn't be modular. So we have to make sure we don't know what's going on. So another quick example is, if we want to do, say, Malloc and free, so seize Malloc and free, Malloc allocates as a block of memory and free takes a block of memory away. And the problem is, if we were just to sort of think of a naive specification, so we start out with nothing and we get a block n long, and then we free it, so we've got a block n long and we get nothing back. But how much does free actually take away? So this specification doesn't say, so I could quite easily give this 1 less or 2 less or 3 less. But actually when you look at the C spec, it says that free will only take blocks that Malloc has allocated, and it deallocates exactly the same size. So how could we do this in a nice way? Because we don't have to give this n in, saying how much it's taking back. Well, what we can do is just use the abstract predicate here. So we represent this kind of extra notion, but Malloc has given us this block. So it returns that we were given a block n long and the block of memory. And free will only take back things that we have a block certificate for. So you can kind of see this as like certificates saying what we were being given and that we can take them back. And this, well, if we do a very naive implementation of Malloc, is kind of very easy to represent, because the sort of basic one in Koenig and Ritchie says, well, in the cell before the block you give them, store the length. So we can just define block of xn to be x minus 1 points to n. So this gives us that we're actually just doing what's going on. The story gets a bit more complicated when you actually look at some of the ones that use doubly linked lists and in-place merging of blocks and stuff. But for very simple ones, it's doable. So,
with that definition, suppose that in the cell X you put the value n minus 1, then would you not also have block x plus 1 n minus 1?
For the module, yes, but block is scoped to being only visible within Malloc and free. So when you're a client, you can't construct a block thing because you don't know what block is.
So, but inside that module, you could then potentially, then you could construct such a block thing.
Yeah.
And then free that, apparently.
Yeah, but the thing, so if you've got these specs, then you're not going to, when you give someone out a block, the thing you take back will be the same size. So you can give other specs and other definitions, So you could give one that gave out block of rets and n, starred with block of ret plus 1, ret minus 1 and n plus 1, if that's what you...
So the correctness depends on that you have to look at all of the places where you construct such a block and destruct it. It's not just enough to have the definition of it.
Because the client can always pass the wrong value for free.
Well, if you give... So, if you want to... So if you're tying it directly against the specification in the C spec and saying you have to meet that, then yes, you have to check that what you're doing actually meets that specification. But you're not going to be able to... you're not going to... With constructing new blocks and giving them out willy-nilly and stuff, you're not going to actually be able to do anything that's wrong, because... yeah, you just can't, because it's sound.
You could just add a check to make sure that the block is a valid block, and that would prevent the user from passing in like the wrong value for free, and it would not work.
Well, that does. Yeah.
But what Rusin was saying is that the client could actually fake it out by putting in the first element.
Oh, no, but it can't, because it's scope. So you can't construct a block unless you're within the scope of the memory manager. So what you do is scope this block definition will be only visible from within the memory manager. So then when you actually come to writing your client code, you can't just assign into x the value n minus 1 and then say, oh, look, I've got this block, let's construct a block thing. You can't do that outside in the client code. You can only do that in the memory manager. Does that...
What would prevent the client to just define their own operation with block as a post-condition, for example?
So the way the rule... So when you combine things, there's certain... The scoping prevents you having the same names combined with different parameters.
Okay.
Well, the other thing that you haven't said is that you need to have the block. Suppose even the client could see the definition, right? When you free a block, of course, it will take away that memory from you, right? And so even if you wrote n minus 1 into the x position, and then you were actually able to transform that x pointer predicate into a block predicate of x plus 1 n minus 1, then sure, you could free that subpart of the block, but then you'd have that block xn left over, and you can't do anything with it because you couldn't use that to free it because you don't have the rest of the necessary memory that you need to prove that. So, so even if you make it available to the client, you cannot really you cannot reuse the memory arbitrarily. You can mess up you can sort of lose some memory to the allocator, but you can't really make any mistakes.
Okay, I can see that how that works now. The specs that you have there in both blue and red, are those the ones that the client of Malloc would actually see, or would the client only see the blue parts?
The client would see that spec because really they want the block of memory to do with what they want.
Right. So then, why does the client care to know about the block ret n? Or I mean, suppose you just deleted that as you did it up above. Then you could just say that the free would just also take the n.
But okay, so do you mean give free an extra parameter? But then that's different from how C's Malloc works.
Now you can truly, well, actually, it's different in the sense that I think Wilson's observation is right. I mean, if provided that you could have the definition of block xn, then you can then you have sort of the same power, right? Is that right? But
yeah.
It's really the abstraction that makes it not possible to fool the memory manager.
Yeah.
Right.
So you want to, when you actually write your C code, you don't think, well, if I store in a value n, and that's the length of this piece of memory, then if I hand that to free, it will work. because you really shouldn't, because there are slightly different implementations, and some have sentinel nodes at both ends, some have doubly linked lists using sort of a couple of sentinel nodes to actually allow combining straight away, and there's lots of different things that can be going on. So this is really about just sort of saying, look, this is kind of a general specification of Malloc and free, which if you obey these specifications, then you should work with all of the sensible implementations of Malloc and free.
And also the point is that what you're doing is you're giving semantics for existing instructions, like free of X already exists. So it would be nice if free would have another parameter, but it doesn't. So you're just giving a semantic to something that exists.
Just one more question. What's the status of the dot dot dots? Are they formal things, or can you express the red things without?
So I don't know if I use it in this talk. I might do later. There's what's called an iterated separating conjunction, which you just give either a set or a range or something, and that's defined. Correct. It was, for simplicity, I wrote dot dot dot, but okay. Any more questions, or shall I move on? Okay, so so far we've seen kind of abstract data types where there's no sharing going on, but one of the kind of common things people do proofs about in Java is list iterators. So where we actually want to share some data. So we have an iterator, and you have several iterators traversing the same list. And you need to know that the pointer that the iterator is thinking about actually points into a place in the list. So you need to somehow tie these things together. But the iterator itself, well, it doesn't really modify the list, it just traverses it. And at some point when you get to modify the list, at least in Java, you end up destroying all the iterators and they start throwing, I forgot what the exception is called, some concurrent modification exception, that's it. So we'd like to be able to do this in our system, but rather than throwing an exception, we just want to actually get to that point and not be able to prove it. So we can write, what? Ah, okay. So the idea here is we need to be able to have some kind of way of having read-only references to things. So far I've talked about this points to. So e.f points to e prime. And that's kind of something that you can only have once. You can't have several people being able to read and write from the same location. So what we're going to do is kind of have a little algebra of these points to's that allows us to talk about being able to only read a location. So we're going to have this e.f read-only e prime. So that says that we can actually read the field e.f, and we know it's got value e prime, and we know no one's going to change that. And the problem is, if we just make it immutable straight away, we can never modify the list. So we need to somehow be able to know when no one's reading it again. So we can do this sort of standard way of doing this, which is reference count, well, read counting. So we count out the number of people who are currently looking at somewhere. So in particular, we can, rather than having just our standard pointers to, we say, well, we point to it, and we know that there's n plus 1 people reading it. And if we have n plus 1 people reading it, and we have a reader, then we actually have the equivalent to there's n people reading it, because we can push it back in. And conversely, if we have it being read by n people, then we can say it's being read by n plus 1 people and get another read permission. So this just simply allows us to take sort of chip bits off it and then put them back on. So there's other models where you can use sort of fractions and sort of split it in a more uniform way, or disjoint sets, or all kinds of things. But this is the sort of simplest one for the example. And we want to make sure that if we're going to be able to modify it, then we can't actually read it. So that must imply false. So writing requires that we have it with 0, and I won't actually bother writing 0 above things normally. And reading only requires this reading permission. So this allows us to have multiple readers, and it prevents us from actually having people both reading and writing at the same time, except if it's the same thing. Yeah, sorry. So let's go back to our example. So if we have a list iterator, so a list normally is something like a list. Okay, so if we have a list being read by n people, so then that's either an empty list, so it's null, or it's a head that's got n people reading it, a tail that's got n people reading it, and the tail is actually a list with n people reading it. And we can think of a read-only list predicate, which is either empty or a read-only reference to the head, a read-only reference to the tail, and a read-only list for the tail. So then an iterator becomes okay, so iterator is just saying, well, the point we're placing into X is a read-only reference to a list, so that's the rest of the list that we've got to iterate through. And we have a list, so this is the magic wand, which is a confusing and bizarre beast, which really means that if I give you something satisfying the left, you get something satisfying the right. So it's like an implication, but it's used with star. So in particular, this thing, so we have list R of X here, and a list Rx here, and a list Ri. So by modus ponens, that really means we have a list I, but it tells us slightly more because it says that X is in the list. So this is a way of, so you could just read list segment there. So you could say we have a list segment from I to X, and this just goes through in the same way. So we're also going to define the second iterator predicate that's ever so slightly different, which just says, and the value we're looking at is not null. So now we can actually go away and specify what an iterator does. So an iterator class requires, to construct an iterator class, we require a list, a read-only list, and if on X, and then we get an iterator on X. If we call, we can call has next with an iterator, and we get, but if it returns a value true, then we get an iterator B, which is one that we'll actually be able to call next on. And if it returns a value false, then we just get an iterator again. And if we have an iterator B, then we can call next on it, and we get back to an iterator. So this just says that we can use these things to iterate through a list. So I'm not actually talking about the contents of a list here, I'm just sort of talking about safety for doing these operations. And by having this iterator B predicate, we get the two-step operation of having to call has next before calling next. So this is kind of defining the protocol by using several predicates. And we can just define the iterator, the list iterator method just to take a list with x, n, and give us a list with n plus 1 and an iterator. So this now means we can kind of chunk out iterators, and this all works quite nicely. But how can we actually modify a list? Because we've started taking out all these things. And we don't really want there to be a kind of dispose my iterator thing, because that doesn't happen in Java. You don't sort of want to do that. And so if we did, we could just sort of say, get rid of iterator, and that takes away the predicate. And then we could say, well, if we want to actually reverse the list, we have to have 0 people iterating the list at the moment, and then we can return a new list that has 0 people iterating it. But this is a bit unsatisfactory, because we really want to be able to just sort of, at the point where we call reverse, kind of swallow up all of the iterator predicates. So what we can do is, so here's the iterator separating conjunction. So this is, if I write this P, then that's just saying I write P n times. So what we can actually say is, well, if we have a list with n people iterating it, and we have n iterator predicates that are all disjoint, then I can reverse the list, and I'll get some new list with 0 people iterating it. So this says that the spec saying we can swallow up all of the bits, all of the people who are currently iterating it in one go, then we can actually change it. So this means that if we've got anyone, so actually if we have a list and we have someone iterating and we reverse it, then we'll have no one traversing it and we won't have this iterator. So when I try to call next, it won't work. So this is where I'd normally get the concurrent modification exception, but here the static verification fails. So this is kind of, well, I think, nice because it mirrors what actually happens in the Java.
One comment though, you said the current model that they not get back to the state, right?
In Java. And here, that's true at the operational level, you don't have to give anything back, but at the predicate level you do. So in some sense, if you then think about your preconditions on your methods, etc., you actually give back the iterator predicate,
Yeah.
so that at the point where you want to modify, you really have gathered all the iterators again. So in some sense, even though at the operational level you don't, you do at the predicate level, and it will sort of mount to the same thing.
Yeah. So in the proof you do, but you don't have to modify your... So if you've written a load of code...
No, but you have to write all your... Yeah, but you have to write the preconditions on your method. So you don't have to have an extra parameter, but you have to have a precondition.
Yeah.
That's
But
like an extra parameter.
yeah. Okay. But when you're actually reasoning about the code sort of informally, you have to know that you're actually going to lose all these iterators if you do this thing. So it's...
So, yeah.
Yeah.
Procedure is going to be very nice.
But across procedures, you'll have to pass these extra iterative predicates around anyway.
Yeah.
And so going with Manuel's comment, so does absence of, so if you called some method instead of that reverse,
Yeah.
and it inside got an enumerator, did a reverse of it, is it going to have to own up to that? And it's,
Yeah.
you for sure will see that in the specification.
Yeah, you'll see that it has to have all of the iterated predicates, otherwise...
So it has to have predicates about everything it does in the heap, like even for predicates that haven't been defined yet. It has to describe exactly everything it does in the heap.
Well, it has to... So if it's going to reverse a list, then it has to have all of the stuff that is required to reverse a list. And that happens, but the specification I've given here to do that requires you to get all of the iterators who are currently traversing that list. So, yeah, you will see that. It might be, you might be able to wrap this up in more abstraction to hide that away. But, yeah.
I was just going to make a similar remark to Manuel there, that it seems that the proof is going to require that you know all the iterators. In fact, it seems that something similar went on with the free from C on the previous slide, where you actually at that point, even though the free does not take the parameter of how many things to free, you need to have it there. You need to.
Yeah.
So in that sense, I think that that the block in that case doesn't actually help much. I mean, you can just imagine that the thing had another parameter anyhow. For example, that the free call had another parameter.
There's a difference, but the extra parameter you can fake it, whereas the predicate you can't.
Yeah.
Yeah, but in fact, I'm not sure that.
The predicate is something you can't pull out of thin air, whereas n you could, right?
If that matters, right?
Well, it does if you want to actually do Malloc and free in C, because they have some very complicated things going on in the background often, where they've got doubly linked lists that are in place, knowing, and sentinel nodes that actually mean they can do compaction of the data in like linear time, which you can't do if you say you're giving back n blocks, then you've got to do a lot more checking and doing.
That the header block contains more information than that, for that.
Yeah, normally it does. I was just giving a simple example for that in that case. And so this is kind of something that does mentally go on when you think about an iterator, that you have to give these things back. So yes, you could sort of start making extra bits of code to do this, but if you actually want to reason about code someone's written, then, well, I'm sort of the opinion that you shouldn't be modifying code to verify it. Okay, so so far everything I said doesn't actually really matter, but I was trying to do anything object-oriented because I haven't done anything other than C structs, really. So when we actually want to do something object-oriented, it's really when we get to inheritance that it starts to look like object. So if we're going to do inheritance in a kind of modular way, we need behavioural subtyping. So I'm going to define behavioural subtyping in a slightly different way. So what I define behavioural subtyping to be is that for the specification of the subtype, we have to be able to derive a specification of a supertype. So this is just a sort of proof-theoretic definition of refinement. So if the subtype's specification using the rule of consequence, the frame rule, any variable manipulation rules you have in Hoare logic allow you to derive the supertype specification, and I'll consider that to be a behavioural subtype. So if you go back to the kind of original thing, Liskov-Wing, then you could just cross out all the other rules and just put the rule of consequence, and then you've got the sort of standard two implications of behavioural subtyping. Because of allowing these variable manipulation rules and framing, we get really something that's very similar to specification inheritance, because it allows you to do more complicated things. In particular, it allows you to do the intersection of specifications. So if we want to consider we want a kind of specification that captures both PC, QC and PD, QD. So we want something that captures both of these specifications. So we can do this by using logical or auxiliary or ghost variables from Hoare logic. So we can say that we've got, our precondition is PC and some logical variable equals 1, or PD and our logical variable equals 2. And then in our postcondition, we have QC and our logical variable equals 1, or QD and our logical variable equals 2. So these are logical variables, so they don't appear in the program. So we know they're never going to change. They're kind of proper logic, the proper variables, rather than program variables. So the semantics of logical variables is really that they're quantified at the level of triples. So we can see this as being for all x, and then this triple. So really, as we're just interested in two particular values of x, well, this is really just the intersection of those two specifications in a sort of semantic way. So using the definition I gave of behavioural subtyping, we can actually derive that. So from that specification, we can derive PC-QC. So we use the frame rule to save the fact that x equals 1 before the call, so it equals it after the call, because we know it's a logical variable, so it can't be mutated. And we've said it's separate, but that doesn't really matter on this. So then using the rule of consequence, we know that if PC and x equals 1, then this is true, because we're just going to inject into this disjunction, we already know x equals 1. And going the other way, if we know x equals 1 and we've got this disjunction, we know we can't be in this branch, so we know we've got this. And then we can hide the fact that we had this logical variable in there away and just get the original specification we want. So this allows us to encode the intersection of specifications. So I think, so in specification inheritance, Levins and Dara, they get this, but they use a slightly, so they have more complicated postconditions where the postcondition mentions old and new state, whereas this is just done purely with Hoare logic and logical variables, but it's a sort of personal choice to which you prefer. So this kind of refinement type thing that we're after for behavioural subtyping, so every class we want the subtype, for every subtype we want its methods to satisfy a refinement of its parent type specifications. But if we do this naively, so if we take sort of a very simple example of subtyping that sort of open Abadi Cardelli, and sort of first example of subtyping is the cell recell. So you have a cell class which has a contents field, and when you set it, sets the contents field to be the value, and then when you get it, it just gives you back the value that was in the contents field. And then recell does the same thing, but it has a backup field as well. So when you set the contents field with set, you actually save the contents that was there in the backup field and put the contents into the contents field, the new value into the contents field, and then you can call get, and that doesn't care about the backup field. And you probably want to add something like undo as well, but I'm not interested in that because that's an extra method which doesn't matter. It's just about overriding that we're going to focus on here. Oh, that's the star saying it's a separate field. Sorry, I'm missing the space. Oh, wrong way. Yeah. Well, it's...
You know x equals 1 is part of it.
Okay, so, so x equals 1 is a kind of what we call a pure fact. So it's something that doesn't actually depend on the heap. So we can spread it everywhere we feel like. So if x equals 1 in this bit of the heap, then it equals it everywhere, because it's kind of a logical truth at that moment. Well, for all time. So, okay.
So then what is the L frame? You can star together something that is not logically false. Is that right? Or could you even star together false?
Well, if you can get false in your precondition, then you can star it. But it has to be something in your precondition. So if you've got false in your precondition, then yes. But most of the time your precondition is not. Okay, so this is kind of the natural sort of specification of cell and resell without any abstraction. And the problem is this just doesn't work, because the way the definition of behavioral subtyping works, this can never be a refinement of this, because it's talking about heaps of different sizes. And we can't, the frame rule won't allow us to do that in the right direction. And the rule of consequence, we can, if one heap implies another heap, then they're the same size. So we just can't get this to work. So we need to add some abstraction in. And even just sort of the abstract predicates I've talked about so far aren't enough, because, well, they're just going to give me two. So if I define this as one predicate and this is a different predicate, then they're just going to be different predicates, so there's no relation between them. So what we need to do is kind of have predicates that are defined on which class they're talking about. So we kind of, the issue with behavioral subtyping is all about dynamic dispatch. So we want predicate definitions that are kind of dynamically dispatched. So if we have e dot some predicate alpha with some parameters e bar, then really what we're saying is there's some definition for a particular class C, and we know E is exactly of type C, then we can just sort of say, well, really we're talking about that definition. So what we get are two rules for manipulating these. So the kind of open and close we had before, where we allow exchange of definitions, requires us to also know that we have the right type. So if we want to say that we have y dot alpha with e bar, and we know y is of type C, then we can exchange that with alpha C's definition. So this means that we can actually use the right definition for that particular class. And conversely, we can do the close operation as well. So this allows us to sort of specify cell, where we can just say, well, we'll have some value predicate to represent the value of the cell, and we can give a specification directly, and then the definition of a predicate is just that x dot contents points to y. So then we can add resell in now. So we'll define it to be, again, on the val predicate, but we give a new definition for resell now that says x dot contents points to y and x dot backup points to z. And here's kind of one of the tricky and awkward bits, that we really need this to have two parameters, because there's kind of two bits going on here, because we want to know about the backup field as well. So what we do is allow, well, that looks horrid. We can, whenever we have an abstract predicate family, we can always throw away some arguments, which is kind of, if you think about sort of when you look at an object and you look at it through a supertype, you sort of think, well, actually I don't care what the other values of the fields are. And then when you kind of think about it back at the subtype level again, you go, well, I know they have some values, but because I was thinking about it as a supertype, I really don't know what's happened to them, because they probably got changed by something. So this So this widen operation takes an abstract predicate family and says, well, we can think about it with some more parameters, but we just don't actually know what values they have. So they're just existentially quantified. So this then, with these two axioms about abstract predicate families, we get that resell set now is a behavioral subtype of set, cell set, and get is already anyway. So this now has allowed us to actually reason about a sensible behavioral subtype.
It's actually quite nice because you now separate behavioral subtyping from actual reuse of code. That essentially my cell I could
use a completely different field. I don't even
Yeah.
have to use X counts, for example. I can just
Yeah.
call my own.
So here, what we put in here can be completely different. We can use other fields. We can misuse fields, because the abstraction we're getting from this says that, well, unless you know this definition, you're not going to actually access these fields. So, and as you go back to the class, it's preventing you to kind of accessing public fields. But you probably, if you're going to change these definitions, you want them to be private fields anyway. Yeah. So, in particular, we can go quite far away, and now we can think about a subtype that really doesn't behave how we want it to. So, if we take the subtype null cell, so we're going to define null cell set to do nothing. It's just going to have some null value, and it will still give us a null value afterwards, no matter what value we set it to. And we define get to always return null. So this is now going to be this really isn't a very good behavioral subtype of cell, because it completely disobeys what cell does. But what we can do is define the value predicate for the null cell to be false. So what this is allowing, it means that everywhere where we're actually going to try and call set with a null cell, we're never going to have a value predicate, because, well, we can never actually get a satisfied instance of the value predicate for a null cell. So there's no way that the code will actually ever be used believing that it is a cell. And we can then intersect in the specifications for cell, but these are vacuous because they'll never actually be called. So although it's doing something completely different, it looks like a behavioral subtype, because the abstraction mechanisms allowed us to completely change the behavior. Okay, so those are kind of very simple examples of inheritance. So a more complex example is the visitor pattern. So this has some complex calling pattern, because we define an abstract syntax tree, and for this, we're going to be a very simple one of constants with integers and plus nodes, which have two subtrees which are both abstract syntax trees. And we'll define an accept that takes a visitor and calls visit C for a constant and calls visit P for a plus node. And then we define a visitor to have two methods, a visit C and a visit P. And this is kind of a very simple visitor pattern. So then we can define a calculate visit, which just sums up everything, as defining visit C. So if it's visiting a constant, it adds a value onto its current total. And if it's visiting a plus, it just calls both. It calls the accept method on both subcalls. So this is using double dispatch here. So it calls accept, which will then call back in to one of the visit calls to get the appropriate static typing. So we don't have to do any casting here, because this double dispatch is doing our case select for us. So this is how object-oriented programmers get ML. So if we want to actually specify this, so we're going to extend our logic a bit just to represent these trees of abstract syntax trees. So we'll have tau to represent either a constant n or an addition of two abstract syntax trees. And we'll also define mu, which is a context. So this is an abstract syntax tree with a single hole in it. So this is kind of representing where we've got to in calculating on this visitor. So then, just for the abstract syntax tree, we define, for the abstract syntax tree class, we define it as false because we never actually want to instantiate one of those. I probably should have had abstract, but that wasn't in my thesis. And then for a constant, we define it to be so a constant x tau, then the value points to n, and n equals tau. And for a plus node, then we say that the left points to the tau L, and the right points to tau R, and tau L, tau R is the appropriate tree. So this is just giving us the data type. So then we can define the specifications for the visitor pattern as, so to visit C, we need to know that the thing we're calling visitor on is a constant, and we also know that we have the abstract syntax predicate, abstract syntax tree predicate for that tree, tau, and we know that we also have a visit, that the thing we were calling visit C on is a visit, we've got the visitor predicate for, and afterwards we have a visited predicate that says we visited X, and X was actually tau, and we did it in a context mu. And visit P is exactly the same but with plus, and then except just says, well, if we have an abstract syntax tree, if we have the predicate for the syntax tree, and we have a visitor that we're calling it with, and afterwards we'll have visited the tree. So we can define these for the calculator as just being, so we define lcalc to be calculate everything left of the whole, and we define calc to be just calculate what the tree contains. So then we define the visitor to say, well, the current amount is everything we've visited so far, everything to the left of the whole, and we define the visited predicate to be everything to the left of the whole and the tree we've just looked at. And we also put in here the abstract syntax tree. So in particular, you might have expected to see star x ast tau in here. But if we were to do that, we wouldn't be able to actually mutate the abstract syntax tree. So for this example, it would be fine because it's a read-only visitor. But if we wanted one that actually changed what the tree looked like, then that wouldn't be flexible enough. Okay, so that's a visitor example. So this is often quite difficult to do because of a sort of callback nature of this code. So in particular, the specs for accept, visit C, and visit P, they're just, the accept methods are just defined once and verified once. And when we do the overriding of visit C and visit P, that's the only thing we have to verify for new classes. So we don't have to verify the other code for the abstract syntax tree. That's all just dealt with automatic, just once. So we've got a modular way of doing this thing.
Can you show me the accept specification again? So here visit. So is the heap the same size as the
But it, so the heap, well, the heap will be either the same or bigger if you've allocated stuff. So you might, and if we were doing this not in Java but in C++, then we might have deallocated stuff as well.
The question is the X half and X is how
They don't contain any heap part, or?
They can, yeah, they do.
Oh, okay, but they get absorbed into visited.
Yeah, so they get absorbed into visited because...
So each subclass of visitor will redefine
yeah.
the AST and the visited predicate.
Not the AST,
Not the
visitor and visited.
Okay.
I perhaps should have used slightly more distinct names for those. But
I see.
yeah, so the reason for this example and a lot of examples, you could just put star x ast tau here, and that would be fine. But if you want to mutate the syntax tree, then you don't want to specify that it has to be the same at the end.
This predicates give you some kind of a flavor of a higher order logic.
Yeah. Yeah, so that's one of my conclusions. Sorry. Okay, so as I'm at Microsoft, I thought I should try and relate my work to Boogie. So here's an example I lifted directly from a paper and then probably got something wrong on. So please don't castrate me too much. So we're going to take two classes, class T and class U. So we're going to say that U's F field is its representation. So this is a field that we consider it to own, and own the object as well that it points to. And we're going to specify some invariant on this that says that the F field G parameter, the F's G parameter, the F's G field is greater than 0, but this is an invariant in the T class. So we can do this in abstract predicate families by defining some Boogie invs. So we define a Boogie invariant on the T class, and this won't take any parameters because there's nothing really exported from this. And that says that the F field points to I, and we own the Boogie invariant of R. And also this Boogie invariant takes a parameter G, and we know that G parameter is greater than or equal to 0. And we define the Boogie inv predicate for the U class. So that all that says is that we've just got this field G, and that's our first argument to the predicate. So this is kind of capturing the same kind of representation and the allowing of tying parameters to get tying fields in our representation to our actual invariant. So where we have unpacks and packs in Boogie, these kind of correspond to where we do open and close with the abstract predicate families. And that's my brief attempt to compare them. I don't know if that's sensible or...
So it seems like you've generalized Boogie in the sense that Boogie has one fixed dispatch predicate, namely predicate for each class. That's
Yeah.
fine. But it's only the only one, whereas your system is defining a number of such dispatch predicates.
Yeah. Yeah.
You could do that on paper using the Boogie methodology as well. That's spectral example. You just write a precondition that talks about the in field without other parameters.
No, but you can only have one invariant in your class, right?
Yeah.
That's one predicate, one dispatch predicate. You cannot have...
Oh, I see. Yeah, I see what you're saying. You want to split one object into several data groups, or
Yeah, I mean, in
yeah,
this
you're right.
methodology, you can have any number of such dispatch
Yeah,
predicates.
yeah.
Okay. So that's pretty much the end of the talk. So some conclusions. So abstract predicates provide reasoning about abstract data types in separation logic, and they seem quite a nice mirror to the sort of standard abstract data type reasoning at the type level, but just by saying, wherever we say type, let's say predicate. So we can allow read sharing, which is particularly useful in a concurrent setting where you want multiple readers on a location. And so there are some difficulties that I haven't gone into here about disjointness, because now star doesn't really mean things are disjoint if they've got read in. But there are ways around this, which I can talk about afterwards. And abstract predicate families, they're kind of really mirroring the idea of dynamic dispatch in the logic. So we actually get a way of reasoning about dynamic dispatch just straight there, so we don't have to play too many tricks once we've got this. And I believe these ideas aren't really just applicable to separation logic, but I haven't really pushed that in a great deal. So some future directions. So the way these predicate families are structured, there's no structure. The subclasses can change them any way they want. So this is quite different to how things occur in Boogie and many other of these things, because there you have restrictions sort of saying you have to preserve the parents invariant, the supertypes invariant, which allow you to inherit methods directly. Whereas one thing I haven't gone into here is if I inherit a method, I have to re-verify that method, because I could have changed the predicate definition in any way. So this isn't very good for library code if you want to inherit from it, because it's practically useless, because you have to change everything. So structuring these things and sort of allowing you to sit in a fragment which allows the arbitrary change, but also allows this kind of nice structure if you need it, is one of my kind of aims to get working. So there's also logical models. So in particular, Noah Torp-Smith, Lars Berkedal, and Bodil Bering have developed a higher order separation logic. And they've shown that abstract predicates, well, as I've forgotten who showed it, but abstract data types are actually existential data types. And they showed that abstract predicates are actually existential predicates. Because you can just, if you have a higher order separation logic, you can just treat them existentially. So a lot of the ideas here, because of this kind of predicate nature, feels quite parametric polymorphism, so it should be quite easy to extend these ideas to generics in a very simple way, but not for the whole of generics. That's one of the things in my 5-year master plan. The main chunk of my 5-year master plan is concurrency. So at the moment I've been looking a lot at non-blocking algorithms and progress properties and sort of hand-over-hand locking and lots of different data structure type things with difficult concurrent properties. And there's also a lot of work sort of in this direction going on about automation. Well, not a lot of work, some work going on about automation. So there's some work on embedding separation logic into COC now, which is kind of fairly in its infancy, but seems to be making some progress. And then there's Smallfoot, which is a project with Cristiano Calcagno and Peter O'Hearn, which they're running that in London now, which is a theorem proof of separation logic, which works really quickly, but does very limited number of things so far, but they're planning to extend it quite a lot. And they have a lot of work they've been doing recently on this is allowing a lot of inference, so actually pulling out loop invariants just out of thin air and magically getting bits of code that I can't even understand and working out what the invariant is. And I think that's my final slide. Thank you.